Yeah, the recording will be available. But also all of the work I'm writing, I will make it into a PDF and will get sent around to you guys if you've given us your email address. So yeah, it is being recorded, but I'll send all of these solutions as well as a PDF. So what I would like is for somebody to work out this number for me. You can use a calculator and then type it in the chat, and somebody else to work out this number for me and type the answer in the chat. So pick one at random and work it out, and let's get it into the chat box. Feel free to grab a calculator. Okay, we have a 5329 and a 3481, a 9050. There can only be two answers, so one of those has got to be wrong. I can see 9050 a couple of times. And a 5329 a couple of times. The first one is 5239. Okay, so proof by democracy. I'm going to say 5329 or 5239. 32, not 23, it's 32. And 9050 on the right-hand side. Yeah, okay, fantastic, very good. So it does appear to be true. In this case, the number we calculated on the left-hand side of the Cauchy-Schwarz inequality really is smaller than the number on the right-hand side of the Cauchy-Schwarz inequality. So we've just made sure that Cauchy-Schwarz definitely works in the case of 1, -7 and 10, -9. Now, we won't worry too much about actually calculating this one, but I just want to show you that it works for lists of numbers of any length. So if we were going to do Cauchy-Schwarz on this one, we should do 9 times 9 plus 9 times -10 plus 3 times 2 plus 14 times 9, and then square that. And then we would also do 9 squared plus 9 squared plus 3 squared plus 14 squared, and multiply that with 9 squared plus -10 squared plus 2 squared plus 9 squared. And the answer you get from the blue stuff would be bigger than the answer you get from the orange stuff every time. So we won't calculate this one. Won't calculate, but you can check. If you like. Okay, we're going to move on and have a look at how to prove some interesting inequalities which are based on the Cauchy-Schwarz inequality. And at the very end, we're going to prove the Cauchy-Schwarz inequality. And the proof is so nice. It's a bit tricky to understand. The notation can be quite hard, but it doesn't use anything you don't know already. It's basically just quadratic equations. So let's go and have a look at something like problem 1. We're told that a squared plus b squared plus c squared is 1. And we're asked to find the maximum possible value of 10a plus 5b plus c. And without Cauchy-Schwarz, that looks really hard. You actually wonder, like, how are these things even connected to each other? How on earth am I going to use any mathematics I know to find the maximum value of this? And what it comes down to, and what's very common in Cauchy-Schwarz problems, is deciding what should be your lists of numbers. So let's go off to the side and just have a think about what our lists of numbers could possibly be in order to get our inequality. And we're asked for the maximum value of this expression. So 10a plus 5b plus c should be smaller than or equal to the maximum value. Now I'll just write down the Cauchy-Schwarz inequality above. x1, y1 plus x2, y2 plus x3, y3 is smaller than or equal to x1 squared plus x2 squared plus x3 squared. My brackets are getting in the way. I'll draw them again later. Times y1 squared plus y2 squared plus y3 squared. So the two lists I'm going to apply Cauchy-Schwarz to, I wonder if anybody in the chat could tell me what would be a good choice for x1, x2, x3. So what should I put here in this first list? 10, 5, and 1. That works because look, that's a really good suggestion. If x is 10, x1 is 10, x2 is 5, and x3 is 1. There's an imaginary 1 there. And then what could we put for the second list? Oh, A, B, C together as y. I see you, Leia. Yes. So A, B, C. And let me just switch colors. So if y1 is A, y2 is B, y3 is C, then we just apply our inequality. So that must be smaller than 10 squared plus 5 squared plus 1 squared times A squared plus B squared plus C squared. And yes, you've spotted it. Remember, A squared plus B squared plus C squared is 1. So this bracket here is just 1. Okay, so 10a plus 5b plus c is smaller than or equal to, that must be 126. That's 100 plus 25 plus 1. 126. Absolutely, yeah. So we found a value it's definitely smaller than, but it said the maximum value, which means there should be a choice of A, B, and C that make the left-hand side exactly equal. So my next question, what could be A, B, and C to make the left side equal exactly 126? Roman, well spotted. 10, 5, and 1 works. Aliona, I don't know if 10, 4, 6 does work. Maybe it does. 10, 4, and 6? Yes, it does. Absolutely. That's a good choice. 10, 5, and 1. Yes, Maxim, I see that. Yep, 10, 5, 1. And the fact is, you can never make it bigger. So if you chose A, B, and C to be anything else, you can never get 126.1 or 126.01. It has to be smaller than or equal to 126. And that's powerful. It's a weird thing to be able to look at this information and work that out. But it's true, and it's all because of the Cauchy-Schwarz. Right then. I'm going to give you a sequence of some examples together then, where it gets increasingly hard to decide what should be the two lists of numbers in order to solve the problem. So here we go. We're given any three numbers, A, B, and C. If you add them together and square the answer, it can never be bigger than 3 times the sum of the numbers squared. Impossible. It doesn't look like the Cauchy-Schwarz inequality, but we can use it. We just need to decide what should be our lists. So if you have a suggestion, or if you want to play around on your paper and have a go to see if you can make a choice of what should go here so that we get this inequality when we plug it into Cauchy-Schwarz. And whilst you do that, I'll just write down the Cauchy-Schwarz inequality again. Good suggestion from Polina in the chat. I see a 1, 2, 3. So that could be one of the lists. What would you put into the other list, Alexander? I see an ABC from Lucy. That looks good as well. That is a good idea, because then we get ABC on the left side. A 1, 1, 1. So we've got some competing ideas. We've got ABC, seems to be pretty common, and then the idea of what should go here. So some possibilities, we've got 1, 1, 1, or 3, 3, 3, or 1, 2, 3, or 2, 4, 6. So just for argument's sake, I'm going to try out that 2, 4, 6, just to see what happens. Doesn't matter if it's wrong, because being wrong is the first step on the way to being right. So let's try that. So on the left-hand side of Cauchy-Schwarz, this would give us 2a plus 4b plus 6c, all squared. And that's starting to not look quite right. The 2, 4, 6 there, I want that to be 1, 1, 1 actually. So let's revise our idea. Let's go back and try 1, 1, 1. And then we get exactly what we want on the left side. What does that leave us with on the right? By the Cauchy-Schwarz inequality, it would have to be a squared plus b squared plus c squared times by 1 squared plus 1 squared plus 1 squared. This gets us 3, and then we have the sum of the squares. Very nice. And if you want to make a bit of money with your friends, what you could do is you could bet them that they can't make the left-hand side bigger than the right-hand side. So say if you add together any 3 numbers and square them, I bet you can't make it bigger than 3 times the sum of the squares of those numbers. And everybody thinks they can, but you can't. Cauchy-Schwarz guarantees it. Here we go. Slightly trickier one. If you take 4 numbers, and you have the square root of AB plus the square root of BC plus the square root of CD plus the square root of DA, and divide it by the sum of those numbers, you can never make it bigger than 1. It's impossible. And you should be thinking a little bit now on your paper or in your head, how is it possible that we can go about proving that this is true? And every example we do today can be solved by Cauchy-Schwarz. So you should be thinking, what should be my lists of numbers in order to make this work? Yes, root A times root A is A. And that's definitely going to help, because when in Cauchy-Schwarz, let's say if we had a root A here, on the right-hand side, it's going to get squared. And that will give us an A. So somebody suggested that the first list, we could have the root of all these numbers like that. And in the right-hand list, I wonder what we could put there. Remember, this number gets times by that number, and this number gets times by that number, and so on the left-hand side. So we've got root A, it's getting times by root B. So let's try root B there. And root B is getting times by root C. So let's try root C there, and so on. So we've got root C times root D. So if we put root D there, and we put root A there, then maybe, if we're lucky, this is going to work. We'll see. Let's give it a go. So on the left-hand side, Cauchy-Schwarz would give us root A times root B, which is root AB, plus root BC, plus root CD, plus the square root of DA. And on the right-hand side of Cauchy-Schwarz, make a bit more room for myself, we end up with root A squared, which is A. Yeah, that was pointed out by Leah. Root B squared, which is B, and so on. Oh, I forgot to square the left side. That's part of Cauchy-Schwarz inequality. I need to square it. Okay. And the sum of the squares of the second vector, well, root B squared, so that one squared, gets me B, and then C, and then D, and then A. That's root A squared at the end. So let's write this out again, simplify a little bit. And you'll notice that this is the same bracket twice. It's just A plus B plus C plus D multiplied by itself. So A plus B plus C plus D all squared. And then finally we square root both sides, and we've got what we want after dividing by A plus B plus C plus D. So I will just finish this off. It's always nice to lay out your solution nice and neat. And then we divide by this thing on both sides, and we have exactly what we want. Done. Okay, the next example I think is probably the hardest example. I think this is the hardest one to see exactly what it is that we need to do in order to make sure we can use the Cauchy-Schwarz to answer it. How about something like that? It's not totally clear. So I'll give you a little bit of time. Until about 1:30, just have a play around. Okay, I'll leave you for another couple of minutes, so keep going. See if you can find a choice for these two lists, which would make the Cauchy-Schwarz inequality become this one. A root, B root, C root. Okay, that seems to make sense because we've got root A times root B plus C. That's another way of writing that there. Root A times root B plus C. B plus C, C plus A, and A plus B. Yeah, you guys are getting really good at this. Cindy, I saw your message. I'll skip back to problem 1 because you think you might have spotted a mistake. Yeah, you guys have picked up the Kosher-Schwarz inequality so fast. This is great. So c plus a and root a plus b, like this. Yes, okay. All right then. Let us substitute that in and just make sure we definitely get what we want. So remember, it was root a times root b plus c plus root b times root c plus a plus root c times root a plus b. Okay, that's on the left side. And on the right side, we're going to have root a squared. So root a squared, which is just a, root b squared is just b, and root c squared is just c. And then root b plus c squared, that's b plus c. Root c plus a squared is c plus a, and root a plus b squared is a plus b. Now we'll simplify the left side. We can put the roots together, so it's root a times b plus c, plus root b times c plus a, plus root c times a plus b. And on the right side, this is where it gets really nice. This here, there's two b's, so that's 2b. There's two c's, so 2c. And we've got a twice, so 2a. And we can factorize out that 2 because it's in every term there. So that becomes 2 times a plus b plus c. But we can simplify that a little bit. We can bring the 2 out to the front, and then this bracket times this bracket, they're the same, so that becomes squared. So it's 2 times a plus b plus c, all squared. Don't I square the left side? I do square the left side. Ah! Well spotted. Yes, I do square the left side. And that is why we end up with root 2 here. So after square rooting, yes, we've got a times b plus c. So we square root both sides. And that becomes root 2 times a plus b plus c. Yeah, I'm glad you spotted that, George, because otherwise I would have been completely stuck and I would have not been able to work out why. Yeah, that's a good thing about working with 75 people watching you. So Cindy, in problem 1, did we square the left side? Yeah, it looks like we did. I think we did. It seems to be okay, Cindy. Unless you meant another one. If you did, then let me know in the chat. Okay, now we're going to use the full power of the Cauchy-Schwarz inequality to prove something really quite deep about any sequence of numbers that adds together to make 1. So if you take any numbers and you add them together to make 1, so any list of numbers that sums to 1, then when you square those numbers and add them together, it cannot be smaller than 1 over n. So let's just see how general that really is. If you take some numbers that add up to give me the number 1, so for example, a half plus a third plus a sixth, yeah, this would be 3 over 6 plus 2 over 6 plus 1 over 6, which is 6 over 6, which is 1. So there's an example of some numbers. It doesn't have to be 3 numbers. You could have any quantity of numbers. Then when we square them, we get 1 over 4 plus 1 over 9 plus 1 over 36. And what we're saying is this number must be bigger than 1 over 3 or equal to 1 over 3, but it can never be smaller than 1 over 3. So let's just check it's true in this case. To get these all over 36, that would be 9 over 36 plus 4 over 36 plus 1 over 36. So that's 14. And we can make that 7 over 18. And compare that with the number 1 over 3, which is 6 over 18. This number is bigger than this number. So we can't make the sum of the squares smaller than 1 over 3. And that's a great and quite deep theorem. Now we're going to try and prove it. And the proof is quite simple. Yes, Maria, yes, 7 over 18. And it's not smaller than 1 over 3. If we have one list with the numbers A1 to AN in there, that's the weirdest AN I've ever drawn in my life. There we go. Then the other vector in our Cauchy-Schwarz should be filled with 1s. Yeah, exactly, sweet Quinn, or Chin. Exactly. So on the left side of Cauchy-Schwarz, we get A1 times 1 plus A2 times 2, and so on, all the way to AN times N squared. Mustn't forget to do that. And on the right side, I get A1 squared, A2 squared, and so on, all the way down to AN. And I also get 1 squared, which is just 1 squared again, and all the way down. And what you have to think is, how many 1s are there? So somebody bash in the chat if you can see. Yes, there are n many, exactly. There are n many 1s there. So on the left side, let's not forget, the sum of these numbers is equal to 1. So this is 1 squared. And you're absolutely right, there are n many 1s here. So that's n times the sum of the squares. And the last thing to do, loads of you got that, that's really good. Last thing to do is just divide by this n. So 1 over n is smaller than or equal to the sum of the squares. And that, to me, this is just beautiful. I can't believe that it's possible to prove something like this using just the Cauchy-Schwarz. It really is the grandfather of all inequalities. Saying that, it doesn't mean that there aren't any others. There are lots of other very important inequalities that you can't prove using just Cauchy-Schwarz. But it is a very important one and really useful. Sometimes if you're going to maybe do some Olympiads or some competitions or whatever, then sometimes Cauchy-Schwarz is a really nice, quick way of proving some inequality that they've given you. But also if you're going to do something like some computer science or even things like sound engineering. I think the question we checked is problem 2. It was the maximum value of 10a plus 5b. Doesn't the second inequality should be 1 squared? So I think, yes, that's 1 squared, but we're lucky because 1 times 1 is 1. So 1 squared is 1. So yeah, that's okay. And Cindy, I think the question we checked was problem 2. Problem 1 was the minimum value of 10a plus 5b plus c. So that one there. Okay, let's double check. Cindy, 10 points to Gryffindor. Are we right? So it'd be root 126. Oh dear. Now, you know what I'm going to say? I did that intentionally just to make sure you were paying attention. That's always what teachers say when they make a mistake like that. Yeah, you're right. This left-hand side always needs to be squared. Yeah. The reason is I'm used to thinking of the right side as being square rooted. But when I was planning to teach this, I think it's easier the first time to think of the left side as being squared. However, now I'm out of the habit of putting the squared on the left side. I always want to put a square root on the right side. So yes, you're absolutely right. Where were we? All right. Okay, so we need to prove this thing. A proof of the Cauchy-Schwarz inequality. Something that we need to understand a little bit about first is quadratic equations. So if you've got a quadratic, I'm going to write it in terms of t. So it's at squared plus bt plus c. And when we plot this, if our quadratic is always bigger than or equal to 0, then it has at most one root. So if we're given a quadratic that's bigger than or equal to 0, it has at most one root. Okay, because we can't pass down into the negative part of the graph. Okay, but this root, if there were one, if it's bigger than 0, you know, it would look like this, and this one would have no roots. Okay, if we were going to be finding the roots, it would be t by the quadratic formula. Okay, so this might be something you're already aware of. This is plus or minus here. So if b squared minus 4ac is a positive number, then it means we can have either the positive or the negative square root, which means we would have two solutions. So in order to have one solution, b squared minus 4ac would have to be 0. And in order to have no solutions, b squared minus 4ac would have to be negative, because we can't square root a negative number. Okay, so on the condition that our quadratic is bigger than or equal to 0, this is true if and only if b squared minus 4ac is either negative, so no solutions, or 0, so exactly one solution. Okay, so it's a very, very brief summary of what we call the quadratic discriminant. And we're going to use that as part of the proof of why the Cauchy-Schwarz inequality is true. You don't have to totally understand this proof. So if you haven't really studied quadratics before and you're not sure about what I'm doing on this page, don't worry too much. You can still use the Cauchy-Schwarz inequality to prove inequalities or whatever you like. Okay? So here we go. I'm going to define a function, f of t, and it's going to be the sum. So I'm using sigma notation to begin with, but I'll write it in list notation after. From 1 to n of the xi numbers minus t times the yi numbers squared. So that's using sigma notation, and don't worry if you haven't seen that before. All it means is f of t is x1 minus t times y1 squared, and the same with x2 and y2 up until we get to xn minus tyn squared. Okay, so we could pick any number t and we could work out this number. However, we are guaranteed that is bigger than or equal to 0. And the reason is, this is a number squared, so it's positive. This is a number squared, so it's positive. We're adding together a load of positive numbers. So of course the answer is going to be bigger than or equal to 0. Okay. Now what we're going to do is open up each one of those brackets. So in sigma notation, that would look like xi squared plus t squared yi squared plus 2, oh, I mean minus 2 times xi t yi. So let's say 2t xi yi. And I'm just going to change the order of these a little bit. So let's move that one down there. Put that one at the end. This one can go at the front, so it looks a bit more like a quadratic. That one can go next, and this one can go at the end like that. Okay, and as a list, you could imagine what that would look like. We would just replace this I here with a 1 to get the first term, and then replace it with a 2 to get the second term, and then all the way up until n to get the last term in that sum. Okay. Now we've got a sum of terms, each of which has got 3 terms in it. We could just do those separately. So we could add together everything with a t squared. And we could add together everything with just a t in it. Can't forget the 2. And then we could add together all of the x numbers that we would get, x1 squared, x2 squared, x3 squared, and so on. Now, all of these terms have got a t squared in them. So we could bring that out to the front and just have t squared times y1 squared plus y2 squared plus plus yn squared. So we can factorize out that common t squared. Okay, and the same goes with the 2t here. Yeah, that could just come out to the front, and we would have x1, y1, x2, y2, all the way to xn, yn with a t at the front, or with a 2t at the front. So minus 2t times that sum there. And this thing at the end we can't really do anything with. Okay, and not to forget, I haven't changed f of t at all. It's still the same function, so it's still bigger than or equal to 0. All I've done is just opened it up. Now, this is a quadratic in terms of t squared. The coefficient of t squared, our a, is this sum here, the sum of the y number squared. The coefficient of t is -2 with this sum, so that comes together to make our b. And the constant coefficient on the end is c. That hasn't got any t in it whatsoever. Okay, now because this quadratic is bigger than or equal to 0, it has at most one root. So b squared minus 4ac must be smaller than or equal to 0. Well, b squared would be -2 times the sum of the xi, yi from 1 to n squared, and minus 4 times a, that's the sum of the yi squared, and c, that's the sum of the xi squared. That's smaller than or equal to 0. Okay, we're close. This 2, that can come in and it can square that sigma, and it can also square this -2. So that becomes 4 times the sigma, or the sum of x1, x2 plus x1, y1 plus x2, y2, and so on, plus xn, yn. And this whole term, we can move over to the right-hand side, just plus it to both sides. And we get 4 times the sum from 1 to n of the y numbers squared times the sum from 1 to n of the x numbers squared. And finally, we divide both sides by positive 4, and we have the Cauchy-Schwarz inequality. Oh, I lost my squared again. There we go. That was that one there. So that says that x1, y1 plus x2, y2 plus da plus xn, yn squared is smaller than or equal to the sum of the y numbers squared and the sum of the x numbers squared. Okay, and that's the Cauchy-Schwarz inequality proved. And what we used was quadratic equations and the quadratic discriminant. And it's a really nice proof. We did use sigma notation through it, otherwise I would have had too much writing to do. But what you can try and do is to write out this proof without sigma notation. You'll need a lot of paper, but if you didn't totally understand, that might help you understand what's going on. Okay. Another thing some of you might like to be made aware of is that the Cauchy-Schwarz inequality is connected to vectors very strongly. So if you haven't studied vectors, don't worry, but those of you who have might be interested to know that if we let the vectors be u and v, then what does Cauchy-Schwarz say? Well, this thing is the dot product. So that's u dot v squared. And here we've got the squares of the magnitudes. So that's the magnitude of the vector v, and that's the magnitude of the vector u. So is smaller than or equal to squared, magnitude of v and the magnitude of u squared. And when we square root, all Cauchy-Schwarz really says is the dot product is smaller than the product of the magnitudes. And if you happen to know that the dot product is u dot v is mod u mod v cos theta, then this becomes really obvious. Because cos theta is smaller than 1. So if I'm timesing something by a number smaller than 1, of course it's smaller than if I just left it alone. So, like I say, if you haven't looked at vectors before, don't worry about this. But just in case you have, that's the connection to vectors. Okay, right. It is 1:53. So that is all of my examples used up. We have come to the end of our study of the Cauchy-Schwarz inequality. Thank you so much for noticing a couple of mistakes. That's really helpful to everybody, and for being so kind and polite about it. It's been a long time in quarantine and my brain isn't working very well. I'm going to leave you with a problem, and I will put my email address into the chat area. And if you think you've managed to solve it, then you can send me your solution. So my problem to you, if you choose to accept it, is using the Cauchy-Schwarz inequality, so using the CS inequality, find and prove the shortest distance from any point on the triangle to the point A. All right, so this is our point A down here. And the triangle is drawn inside a unit cube. So that's side length 1, that's got length 1, and that's got length 1. And at first glance, this might seem like geometrically obvious. If you take the middle of the triangle, then that should definitely give you the shortest distance. And that feels really obvious. If you move the point on the triangle this way, then the green line should just get longer. So the shortest should be when we're in the middle of the triangle. But that's just looking at the picture. That's not a mathematical proof. So we're going to need to use Cauchy-Schwarz. Well, we don't have to, but it's fun. I want you to try and use Cauchy-Schwarz if you possibly can to prove that the shortest possible distance is given when we're in the center of the triangle. If I moved over here, it's longer. Yeah, so find and prove the minimum of D. All right, that's it. It was lovely chatting. I'm around for another 5 or 10 minutes if you want to ask any questions. Preferably mathematic. I'm glad you liked it. I think it's Alexander Morpos. Yeah. Which year is this for? It's a good question. So, I mean, you really, in the UK at least, you just study this at university. But when you're preparing for competitions, you quite often study the Cauchy-Schwarz. Yes, I'll send a link to the recording to anybody who was signed up. What other applications in physics? So, geometrically, if you've got two vectors, u and v, then when you project one vector onto another, that's using the dot product. And so you can do things like with forces, you can prove that the component of a force in any direction other than its own direction will always be smaller. That kind of thing. Oh yeah, sure. My email, I'm just popping it in the chat here. This is my college email. So when you think you have a solution to our problem, then you can email it to me there. And I'll give you some feedback on your solution. Also, if you're working on it and you get stuck and you want to see my solution, then go ahead. It's my pleasure, Anastasia. I'm glad you enjoyed it. So yeah, you formally learn this at university, but there's no reason that you can't understand it at this age. And it does turn up in like the Maths Olympiads in the UK. Yeah. Thank you, IC Wang. It was lovely to have you. Thanks for all your film suggestions. I'm going to go and watch some of those Russian movies now. Thanks, Sophia. Nice to see you. Thanks, Leah. Thank you, Maria. You have the link to the recording and the PDF I'm going to send through. It might take a couple of hours because it takes some time to upload. Cheers, John T. Thanks, Yvonne. See you later, Ivan. Bye, Nadia. That's no problem, Tina. It's okay not to understand stuff the first time. It's totally normal. I don't usually understand lectures I go to until I go back and look at my notes again and play around with it a little bit. Leah, I do. I work at the National Mathematics and Science College. So let me pop in a link. They'll put a link to the college I work at there so you can take a look. There you go. I'll see you later. Thanks, Roman. Bye-bye. It's in Coventry in the UK, Leah. and it specializes around maths and science. Bye, Alexander. See you later. I should stop the recording. There's just 10 minutes of me saying goodbye to people at the end of the recording.